Okay. Good morning, everyone. My name is João Carvalho, and this is the title of my work, Structural Optimization for Mass Estimation of Large Aspect Ratio Wings with Distributed Hybrid Propulsion. And it is deeply correlated with European project Indigo, whose PI is Professor Rano Cavallaro from this aerospace department. Okay, so basically, the motivation of this work and of this project is deeply connected with the European goal to basically achieve carbon neutrality in the next few years. And as this graph from Aerocontrol shows, the forecast is that the number of flights is going to increase, and therefore, basically, meeting these environmental requirements will be harder and harder as the time flies by. So basically, driven by these environmental constraints, the design is driving to wings with increasingly high aspect ratios. And basically, by increasing the aspect ratio, although we can have wings with lower drags and higher aerodynamic efficiencies, there is also a very high weight penalty associated, especially when considering cantilever wings. And therefore, basically, to minimize this weight problem, Indigo proposes a straight braced wing configuration, which is displayed in the lower part of the slide, that basically consists on two wings, a main wing and a second one denominated strut that basically supports the primary one, and whose idea is basically to decrease the bending moment felt on the root of the wing. Okay, so basically my part in this project and part of my work is to find a way to estimate the weight to feed an MDO framework. And usually in aerospace engineering, there are already empirical methods which were generated using data and experience from a lot of aircraft. But since this is an unconventional configuration, that data does not exist, and therefore we were forced to generate a physical model to have and to supply to the consortium to a mass estimation which is more reliable. Okay, so basically to do that, we developed a tool which is an automatic parametric finite element model generation, and whose ingredients, whose recipe is basically presented here, and these are the several ingredients to basically cook this framework. So the first one is obviously parameterizing the structure and defining it, and also define the materials and properties. Then discretize the structure and store the elements by tag and by components. And then a third step where basically we assign the respective properties and materials to those elements, and we define local coordinate systems and material orientations, which is kind of important when we are talking about composite materials. And then we also need to take into consideration non-structural masses, such as, for instance, the masses of the electric motors and turboprop, since we are talking about a wing with distributed propulsion. In the end, basically the last step is to apply the correct boundary conditions and the appropriate external loads to supply reliable mass estimation. Okay, so with this framework, we reached the design phase, and in this project, basically this is the wing plan form that we considered. So a wing with a straight leading edge that starts to taper after the middle of the semi-span. And these are already the two versions that we have designed so far. So Indy 1 is version 1, and Indy 2 is the version that is now being currently analyzed. Although they seem very similar, there are a lot of differences between them. But due to time constraints, I will basically try to focus on some of the details that I think are more important. So basically, the wing fuselage connection is based on a high wing configuration. So that double lug connection that you can see on the left, you can find, for instance, on an ATR 72. and both versions share this multi-spar bay connecting the wing to the strut to basically better redistribute the load coming from the strut to the wing and vice versa. On version 1, the option was basically to prolong the wing box coming from the strut entering the fuselage, and the spars of that wing box are connected to the fuselage frames to also better distribute the load and achieving a lightweight structure. Okay, so focus on version 2. Basically, I think that the most important difference is the landing gear integration. So what it did here was a complete redesign of the connection between the strut and the fuselage. And now this connection has not only a structural function to transfer the loads from the strut to the fuselage and vice versa, but also to store the landing gear when it's retracted. Okay, so basically this design was based on conceptual aircraft design formulas to also guarantee the aircraft longitudinal and stability considering ground maneuvers, but also taking into consideration that, for instance, the span-wise distance between the landing gear and between the two wheels of the landing gear, since this is a tricycle configuration, should also be minimized to basically designing a fairing that would not compromise the aerodynamic performance of the aircraft. Okay, so basically this is the overview of this outer mold line which has been frozen, and as you can see the structure fits perfectly inside the fairings which have been designed in the last 2 or 3 weeks. Okay, so with this methodology we have the framework developed, the design, and now we need to basically do the structural sizing to basically estimate and provide the mass to our partners. Okay, and that was done considering a design optimization, so a structural optimization whose objective function is to minimize the mass. The design variables are the respective thicknesses, and then this optimization is obviously subjected to several constraints, not only in terms of thickness to both composite and metal, but also considering composite manufacturing constraints and also the usual strain constraints which are different for composite and metal, and buckling constraints. Focusing on the composite sizing constraints, basically we considered a discrete ply thickness and a maximum total stack thickness below 75 millimeters to basically guarantee that that region can be manufacturable, and then we fixed the ply share constraints in each component, and basically these percentages were obtained from real commercial aircraft, and basically what they do is they diminish the number of design variables, so making the computational cost more affordable, and basically we believe that they can give us a more reliable mass estimation. Okay, so to finalize, it's the parameterization. So basically what we did was we divided the wing in several regions, and what you can see there is an example of a wing box which was divided in several regions, and I present there also the ply properties that we consider and the aluminium properties too. Okay, so having this methodology, we basically just need to apply it to a real case. I will here today just show the results considering the version 1. Well, basically I used this framework with these input geometrical parameters to generate this strut-braced wing, and what I show here are the boundary conditions that we considered. So asymmetry boundary condition in the mid of the fuselage, so all the elements in that axis are basically have a symmetry boundary condition, and then I define the spherical joints connecting the strut to the strut fuselage connection, and hinges in the double lug connection between the fuselage and the wing. Okay, taking that into account, we basically did this optimization not only for the strut braced wing, but to an equivalent cantilever wing, considering both aluminium and carbon. And as you can see, we can achieve high weight savings, considering this strut braced wing configuration for this aspect ratio. And we can also observe that the use of composite materials enhances the potential of this configuration to basically minimize the weight. I will basically finish this presentation with some optimal thickness distributions. So these are the thickness distributions that I obtained for the wing, and they are basically in accordance with results published in the literature. So the trend is basically that the thickness decreases from the root to the tip, and then we have, for instance, on the spar a bit of discontinuity due to the connection between fuselage and wing with that lug there. And then we have a more chaotic behavior, let's say, in the strut braced wing configuration. Due to the large interaction between the structural behavior of the strut and wing, it is not as predictable as the cantilever wing. Nevertheless, I show this slide basically to identify one of the structural challenges of this configuration, which is the connection between the wing and the strut. So as you can see here, the higher thicknesses are concentrated in that region, and that is why we had to basically consider a multi-spar bay region there to basically has the possibility to have thicknesses that could be manufacturable using composite materials. Okay, so with this, I basically finish my presentation. These are basically just the key points: the structural efficiency potential of this configuration when considering high aspect ratios, the importance of physics-based weight estimation models, the manufacturing challenges, especially in that region between the wing and the strut, and then the composite potential to enhance the weight saving potential of this configuration. And this is so far my contribution to the literature. So guys, thank you very much.
Okay, João.